Hello, everyone. I think we are going to be starting. It's 10:05, so we were waiting for some people connecting, but I think we can start now. So I'm really happy to be here with you in this last episode of our series of workshop in actually dedicated to protein localization in high resolution. This is our last episode, and we will be talking about correlative light and electron microscopy. So what is exactly CLEM? It's very simple. It's a combination of two microscopy modalities. One is coming from the light microscopy and another for electron microscopy. And it's not a unique technique. It's an accumulation of different techniques. So you obtain more data and thus more information. Actually, the information is coming from the light microscopy is a specific information of your sample, is from your protein of interest and your organelle of interest. And then you use the electron microscopy actually to give in an infrastructural context. As you can imagine, the sample preparation for this kind of methods needs to be compatible for electron microscopy sample preparation. So the most part of the people that they develop these methods have a really high expertise in electron microscopy. The only drawback of this method, which is not trivial, is that it's very time consuming and can be pretty expensive because of the equipment you need. And if you don't have this kind of equipment in your labs, it's not cheap. So these methods have been developed for a while now. They started the first protocol I found is in the 69. In this article that it was more dedicated to clinic research, but the last developments and the most important developments, please turn off your microphone. The most important developments has been in the last decade, actually, because thanks to the development of new pros dedicated for CLEM, also in the appearance of new resins and new protocols for CLEM, and of course the development of dedicated system exclusively for correlative microscopy. So since then on, in 2012, started to appear these beautiful booklets about the different protocols in correlative light and electron microscopy, and they are updated every 2-3 years. And also the community has been getting together in Europe to create a compendium of the different modalities in electron and light microscopy, and also for research in biological research and in clinical research. So today we are working about the workflows we do in the BIC. We will be talking to different people. So you will be able to make some questions after the end of the different protocols. So please, if you want to ask something, write it in the chat, and we will be talking about this question at the end of each presentation, okay? So the CLEM workflows, it can be divided into categories depending on the sample preparation for electron microscopy. There is the methods in room temperature, where the biological specimen is fixed by chemical fixation, and then the classical sample preparation for electron microscopy. And then also we can cryofixate the sample that can be really observed directly in cryo-electron tomography. Depending on the size, also they need some cryosectioning. Of course, we can pass by these protocols from cryofixation to sectioning after free substitution and embedding in different resins. That is very practical for CLEM, as you will see. And the labeling of these specimens in fluorescence, we have been we had a dedicated workshop for these labeling techniques and for electron microscopy. You can follow it in the YouTube channel. But this actually you can label it at the beginning of the preparation. Also after chemical fixation, what is called the pre-embedding immunolabeling, and after section also, which is called the post-embedding immunolabeling. The imaging of fluorescence, you can do it in live imaging before doing all the preparation. You can do light microscopy after chemical fixation, but also at the end after sectioning of your samples. At the Bordeaux Imaging Center, we will be talking about the different protocols we have available for the users. So Sabrina Lacomme will be presenting the classical CLEM preparation for 2D, which use the light microscopy to find the region of interest, and then sample preparation to observe either in scanning electron microscopy and transmission electron microscopy. And she has different protocols to share with you. Then Clément Chambaud will be explaining the resin fluorescence protocols, where they take the advantage of different resins after cryofixation that preserves both fluorescence and immunoantigenicity, so they can observe the fluorescence of these sections before going to electron microscopy and target the region of interest. Then Melina Petrel will be starting work talking about the 3D CLEM, where they have really advanced microscopes and protocols to first do the 3D reconstruction from the images from hundreds of sections, serial sections, both in light and in electron microscopy, and then to be able to correlate them and what are the strategies is taking. In the same time, also a 3D CLEM protocol, very important here in the lab, is the use of a serial block phase microscope, where they have ultramicrotome integrated inside of the chamber, and they use a light microscopy actually to mark the tissue and the region of interest, to be able to pass it in the microscope and then 3D reconstruction. And finally, I'll be talking about the Cryo-CLEM protocols, which is the more direct workflow from fluorescent specimen. You cryofixate the specimen. You can observe it directly by light microscopy and electron microscopy in cryogenic conditions. So these are some of the software solutions we find, but it's going to be more specific of each of the protocols you will see. But we use regularly use the EC-CLEM plugin from the IC software that to do image registration with different scales of the images, and you can calculate the error and the image calculation correlation. Atlas 5 from size, it serves actually to register the coordinates of the different observations in light, and that this serves also to automate the electron microscopy acquisition, and this is the same for serial EM, which finds the coordinates of the registration of the light microscopy, and then you can do automated tomography acquisitions. And of course, you can go to different sources of information and national and European hubs like in bioimaging. So they also offer training and access to microscopy facilities, and they give you grants for technological transfer. And there is the big community in CLEM and correlated multimodal imaging, actually, that they offer also training grants and short-term scientific missions. If you are interested in developing some techniques, you can have some money to go to different facilities. So I finished to do this introduction. Of course, what I said, you can ask and send an email if you want to know what workflow do you need for your project. If you have any questions, you can do it now. And but if not, we can pass and start with the different workshops and the different workflows for explaining.
Hello, everybody. So I'm going to speak about 2D CLEM and why we use it, and how technically we proceed to do that, showing you some application treated on the platform. So the idea of the correlative is used light microscopy and electron microscopy to combine advantages of both techniques and allow us to observe the same object or the same event using a tracking system. So how it works technically, so we start with a 2D cell culture. Then we do an immunolabeling, and we observe in light microscopy and localize a region of interest. Then we treat the same sample for the electron microscopy and we image. And the aim is to localize the same region of interest in order to analyze at high magnification and obtain the ultrastructural context. So you understand that the key of this technique is the capacity to localize the same region of interest. And to do that, we use several supports on which the culture will be made. And all these supports have a simple mechanism, an alphanumeric pattern to identify the exact position of the point of interest. So for example, on glass cover slip, there is some numeric pattern from 1 to 99. It's an engraving. And on Aclar and Sapphire disc, we do ourselves a carbon replica from a grid or from a disc with an alphanumeric pattern. And this carbon replica plays a role of the pattern. And so with this alphanumeric pattern, we are able to localize the same number or the same letter, and so the region of interest. Of course, the immunolabeling is another tracer for us, for help us. So the immunolabeling is made in pre or post embedding. Generally, in light microscopy, transfected cells expressing fluorescence protein are used, or a classic fluo immunolabeling. For the electron microscopy, we use dense gold beads. Gold beads. So in this case, the fluoro nanogold offers a good compromise for the CLEM because it's detectable with both microscopy. But even if on the paper it's a very good antibody, in reality it's a lot of controversy because it's not a robust antibody. But I don't explain more because I think during the workshop of during the first workshop of the session 2 with the immunolabeling and ultrastructure, we speak about fluoro nanogold. So now I'm going to show you several workflows used on the platform, and so the first one, it's a combination between light microscopy and scanning electron microscope. So we use this workflow on a project on cells coating on collagen fibers. So technically, the culture was performed on cover slip, on glass cover slip, so with the numeric pattern. And after chemical fixation and light microscopy immunolabeling, the culture was observed in light microscopy in confocal, exactly, and the region of interest was localized. And then the same cover slip was treated with a conventional preparation for SEM, so with dehydration, with solvent, critical point drying, and platinum coating. And then observe in SEM, the same region of interest is localized and the correlation was done. So on the results, so on the confocal image, we can visualize the number of the pattern and the different cells with the immunolabeling. And the SEM, the aim is to localize the same, same number of interest, so the same area, and with the shape of the cells we are able to correlate and to merge both pictures. At high magnification, the interest of this technique is to localize a precise region where there is the immunolabeling. So here, the group of collagen fibers are interested for us. And the results show the interest of the CLEM, because here in this case, we have a group of several fibers, and only one fiber present the immunolabeling, and at high magnification in SEM, we localize the vesicles of interest. So the region number 2 presents this event and not the region number 1. So here you can visualize the power of the correlative. On the second workflow, it's a combination between light microscopy and TEM with a process at room temperature. So this application was used for a study of chronic pain mechanism. So at the beginning, we have a culture of transfected cells, so GABA-B1 GAFP, performed on glass clover slip. And after chemical fixation and immunolabeling with using fluoronanogold as a secondary antibody, we observed in light microscopy and localized another number region. After that, the cover slip was treated for TEM. So for TEM, we do silver enhancement first, because we use when we use an immunolabeling in pre-embedding, we use gold bits around 0.6 to 1.4 nanometers. So very, with a low size, sorry. And in TEM, it's not easy to localize, so that's why we increase the size of the bits by a silver enhancement around 10 to 15 nanometer. So after this enhancement, the process is classical, so dehydration with solvent and epoxy embedding. And after polymerization, we are able to localize at the surface of the block the number of the pattern. So this is possible because at the surface of the cover slip, the glass cover slip, there is an engraving, so in positive and negative relief. So when we add the resin, the epoxy fill this engraving, and when we remove the block to the support, we visualize the number in relief at the surface of the block. So we are able to do sectioning in the good square of interest. So it's not the same number, but I don't have the good picture, so sorry for that. But you understand the principle. We do sectioning only in the good region of interest. We deposit on slot grid, and we observe in TEM. So as you can see in the result, at low magnification, in the TEM picture, we can correlate with the light microscopy picture. And thanks to the shape of the cells, we are able to localize precisely the cells of interest. And at high magnification, of course, the immunolabeling helps us to determine the cells of interest and to give us the ultrastructural context. We can see the research protein of interest. On the third workflow, it's a combination with light microscopy and TEM at room temperature too. But in this case, this technique is the most simple way that we can use without any specific support. In this case, we use micro pattern, homemade micro pattern in the case of the study of synaptic protein interactions. So we use the ACLA and we did manual streaks with scalpel, and the culture was made on this support. So after fixation, immunolabeling, striped gold, we localize in light microscopy the ACLA, and we can recognize the region by the streaks and the immunolabeling on cells. So after the same treatment for electron microscopy that I previously explained, we obtain a block, and in the block, we are able to localize the same square, so this square of interest, and do sectioning in this part only. So in this case, we did transversal section because the protein of interest, the aim of the study is to look to analyze the interaction between cells and support. So that's why we did transversal sections. And so as a result, we visualize the gold beads at very high magnification to obtain the ultrastructural context of the same ROI. And the last workflow I would like to show you. So I don't have any application for this, but it's a workflow that we can do on the platform too. So it's a combination between light microscopy and TEM using cryofixation first. So for that, generally culture was made on a sapphire disc with a carbon replica. So a culture of transfected cells. Then after live imaging and localization of a region of interest, we do high pressure freezing, free substitution, and acrylic embedding. And after polymerization and removal of the block, this is the same principle as during the engraving I explained you previously, because the carbon replica stay at the surface of the block, so we are able to localize the same region of interest and cut only in this part, do serial section. And after section, gold immunolabeling in post-embedding was made using gold beads around between 5 to 15 nanometer, and an observation in TEM for the correlation. So to resume the several workflow, I think you understand that the principal interest of the correlative, the 2D correlative, is to discriminate a weakly represented object or two very closed objects with a precise localization due to this pattern. And of course, all the several workflow that I explained you today are mastered technique on the platform, and you can obtain quick results. But of course, into the CLEM, the limitation are generally due to the culture, the quality of the culture and the density of cells. For example, if we have a lot of density of the culture, sometimes it's impossible to localize the number of interest at the surface of the cover slip. So it's difficult to correlate precisely the same region. And of course, when you would like to combine immunolabeling and ultrastructure, you must do some compromise. So for to compromise to obtain the best results. So I don't explain in details because you can visualize the replay of the workshop done last year, if I remember, the episode one, session 2, with the immunolabeling and infrastructure. So, and another limitation with the correlation is the difficulty to combine properly both image. So that's why Mónica talked about some software like BIC-CLEM, for example, and this software facilitates a lot the correlation and can help us. So I have finished for this talk about 2D CLEM. So I would like to thank you for your attention, and I would like to thank you, the participating teams too.
Yes, it's okay. So now we will speak about another method, which is use the capacity to keep the fluorescence during the TEM sample preparation. Because the implant is very difficult, it's impossible to have, in fact, adherent sample. So we have to keep the fluorescence during the sample preparation to be able to target the region of interest. And I let Clément to explain you this part because it was the subject of his PhD, and he takes he used a lot of time to manage this technique.
Okay, so hello everyone. So then I will do a quick introduction about why correlative microscopy. So already the previous presenter have already explained, but in our project we were grafting Arabidopsis, and when we graft Arabidopsis, then it formed a bunch of undifferentiated callus cells. And as I was interested in the ultrastructural event that were ongoing at the graft interface, I would have to implement correlative microscopy to target those events and be able to access the ultrastructure. So when you have this, the first step is to find a solution to find the graft interface, because where exactly is the graft interface in this bunch of cells? So this first step was to choose different fluorescent protein for the two parts of the graft, the scion and the rootstock. And as you can see here, we were able to find first on fluorescence microscopy to be able to differentiate the cell at the graft interface. But as you know, fluorescence microscopy doesn't permit to access to the ultrastructure. And on the ultrastructure under electron microscope, transmission electron microscope, then you lose this information about fluorescence. And again, you have your bunch of undifferentiated callus cells where you couldn't find the graft interface. So the idea is to preserve the fluorescence throughout the sample preparation and be able to combine the two techniques and get both advantages of the two techniques and find again the graft interface.
Now you can see the second sticker.
Okay, so where I was. So the idea is to combine the two techniques to get advantage of both of them and find the graft interface, and then study the ultrastructure and ultrastructural events ongoing at the graft interface. So the workflow, we are gonna present the workflow. There is several critical steps that I resume in this little scheme, but we are going to present more in detail each steps. So our method, the in-resin fluorescence, is adapted for plant sample from this paper from Kukulski, which is available for yeast and mammals. But for plants, we need to make a lot of adjustments that took a long time and long process to be able to get good results. So I would say that the first step was to choose the good fluorescent protein. Higher? Okay, I need to speak higher apparently. So to choose the good fluorescent protein, there is many criteria to take into account. And the first is to have a good signal at first. Okay, to have a good signal at first. So I will recommend to have a strong expression. So in your samples, either plant or whatever your sample is.
Yeah, it's difficult to give you an exact number of that, but you have to can observe very easily your signal with your microscope. Okay.
So yeah, it's best to check your signal before the fixation, because as it's a long process, if you have nothing at first, then don't start. So for us, we know that our protocol works with EGFP, YFP, MRFP, TAG RFP, BFP, and M Scarlet.
I have a question. Do you have a problem with one fluorochrome? In fact, it works with everything.
Apparently, it works with a lot of things, but it seems to work better with red fluorescent protein.
Okay.
Because the signal apparently is more preserved along the process for red fluorescent protein. This might be explained by the properties of fluorescent protein, such as the pKa's and pH of resin and such characteristics.
Yes.
But don't worry, if you have a 2-week signal after the fixation, remember that the protocol is compatible with immunofluorescence and immunolabeling in general, for example, immunogold also. So your signal could be amplified. So as you know, maybe, when you prepare a sample for electron microscopy, the conventional techniques use a lot of chemicals such as osmium tetroxide and glutaraldehyde. And those components, those fixative agents, they quench fluorescence or they generate a lot of background noise. And so they are not compatible with our technique. So we have to avoid the use of this component. And to do so, we use Cryo methods. And also, compared to standard Cryo methods protocol we use in plant, we reduced the time for freeze substitution to expose less the fluorescence protein to chemicals. So we use the HM20 resin, which is a nice resin because it's compatible with cryo methods, and it polymerizes at -50, which is very important because we don't use fixative agents. So we have to keep our sample in cold at every moment. Plus, this is very important for the following part. It is compatible with electron tomography, which is give us very nice images. And then it's not last but not least, it's a resin that is quite easy to handle. So we like things when it's easy because it's not always like this.
Just I can add one point.
Yeah.
HM20 is very acid, in fact, and we think maybe that it could be due these properties that explain why fluorochrome with a low pKa could be better for in-resin fluorescence approach.
Okay. So now as we are using HM20 that's polymerized under UV, we decided to reduce the UV exposure to its maximum to minimize photo bleaching. photooxidation. So this is, should be the other part. Okay. But well, the general idea is also to, if we reduce the time of polymerization, we also reduce the time where the fluorescent protein are exposed to the liquid resin, I would say, to the solvent. And we want to reduce the photo bleaching to its maximum, and with our methods, depending on the volume of the resin you use for your resin block, you can go between 10 hours and 36 hours of polymerization. And it's the limit, because below this limit, the resin will be too soft to cut. And yeah, above it, it may work, but try to reduce the exposure to UV in case. And after, this is a very important part, is you have to keep your resin samples in the dark at minus 10, 20 to reduce the speed of oxidation. We noticed that the sample we made like a few years before, a few years ago, the fluorescence is less visible. So when you do your fixation, try to process when you can your resin samples and not store them too long.
And we have also the feeling that the surface of the block is less conserved than the deeper part of the sample. In fact, it's like if on the surface the oxidation is most important.
Yeah. Okay. So now we have to optimize the thickness of section, and this is actually to optimize the fluorescence visibility. What you have to think is when you cut your sample, the more thick is the thicker is the section, the more photons will be available in the section. So you have to adapt the section thickness. Usually what is used for having a good infrastructure is a very thin section, which are between 60 and 80 nanometers. But these could be too weak to be, so the fluorescence can be detected at the fluorescence microscope. So don't throw your samples, because by increasing the section up to 150 nanometers with a regular 120 kV electron microscope, then you can have a good result and good infrastructure, and this may be sufficient to see your fluorescence. And remember that with higher tension, then you can even increase the sections. And this is crucial and important. To avoid oxidation, you have to make your section just before confocal imaging. This is better. Again, to optimize fluorescence visualization, you have to take care about not having air bubbles when you mount your sample between grid and cover slip. This is a tricky part. And remember to mount your samples always facing up. This can help in two steps, I would say, because you will see the shape of your cells even on top of the grids. This could give you information. And plus, if you you mount your samples at the exact same way each time, it will be easier when you go to the electron microscope to find again the same orientation of your sample, which is better.
Because sometimes it's not very easy to turn the screen of your computer.
Okay, so to mount your sample, you need those basic elements, which is a pair of tweezers, water that you filter to not make particle and dust on top of your grid, and of course the grid and slide and cover slip.
Very clean. You have to.
So here is a little video on how I'm doing. So I'm putting a little drop of water. Then I'm taking the grid out of my box. Always put the grid in the same way in the box so I know where my sample is. I'm putting a little drop of water onto the grid at each side of the grid Then I'm taking the cover slip and I'm putting the grid into the water. And I'm maintaining the grid with the tip of my tweezers, so I can put my my grids into the water and then release carefully. Then you can remove the excess of water and go to the confocal microscope.
Because here the point which is very important is to see that the water goes up to the section. You have to avoid to have just water around your grids. So it's very important to cover your grids with water.
Yeah, because you have to remember that HM20 is hydrophobic. So the water will not go onto your sample. So you have to force your sample to go into the water and then put the cover slip that will maintain the sample into the water. Okay. So the next step is to go to the confocal microscope. And even if you think that a section is flat, then it's not completely flat, as you can see. So we are doing a Z-stack acquisition. And to optimize the visualization, then we are doing either a maximal projection or some projection to have a sort of flat images. And then, as you can see, we can see the graph interface. And last step, not the last, but a very, very crucial step, it's the unmounting step. And you have to not destroy your grid, because if you are imaging too long, then the water is drying and the grid is completely stuck to the cover slip and to the slide. So if it's stuck and you remove it too fast, then you will break your sample and you've done the imaging for nothing. So to do that, I'm adding a bit of water, and you have to see that the cover slip is unstick with the water again. And you do it slowly. You remove to the side, and then you take a corner, and then you remove the cover slip. And then you add a bit more water to be sure that the grid is not stuck to the slide. And then you can take out and eventually dry the grid. And be patient and wait until the grid is floating, because if you're going too fast, then
you remember?
It's gonna be a mess. Okay, so this is the recap of all these steps. So strong signal, strong expression, good choice of the fluorescence protein. Then you have to reduce the exposure to chemical agent by avoiding those fixative and using cryo methods. Then you reduce the UV exposure to its maximum. You have to choose and optimize the section you need for imaging. And then you can have you have to avoid air bubbles during mounting and do Z-stack acquisition to be sure to collect all photons available in the section. And of course, you can do a loop. If all those parameters, you can readjust, start from the beginning, choose other fluorescent protein, and etc.
And one point which is very important is for us, it's to use a very performant optical system, very sensitive, because it can change everything.
So now I'm just showing a few. So there is this after. So remember that CLEM is very powerful but challenging. And so in our case on graft, if I'm starting from 100 samples, I'm losing samples at each time. And in the end, I just have a few samples in resin block. So always remember, don't be desperate. It's a challenging method, but it really worth it because it can give you a very nice result. So here it's an image with confocal imaging. We have the same image, same region under electron microscope. And then you can do the correlation and be able to find your graph interface or your region of interest. And focus on different region and access to very fine ultrastructure like this.
And you see, we don't have a lot of details due to the important thickness of the section. And
yeah, how can we improve this resolution now? If you remember well, at the beginning of my talk, I said we can use our method for electron tomography. And this is how we'll compensate the 6th section, I would say. So first, for correlation, I'm using IC and the EC-CLEM plugin, but I won't go into detail because there will be another part for that, I guess. No?
No.
No. So yeah. So basically, I'm using this software, which I find quite easy to use, I guess. And we are using a natural landmarks such as nuclei, mitochondria, shape of the cell, plastid, and whatever can be recognizable. But you have to remember that you can use fiducial that are visible in both fluorescence and electron microscopy, such as tetraspec, PSF check, and whatever you want. So what I'm doing at the acquisition, I'm always acquiring tiles, either at confocal and electron microscope that I'm merging to have a big region of interest that help me to have the whole graph interface and more element to correlate so the alignment is good in the end. So now I will talk about electron tomography. This is to compensate the big section we have. What you have to remember is when you're at the transmission electron microscopy, the image you get is a 2D projection of a 3D object. And by acquiring a series of images and reconstruct those series through different algorithms, you can reconstruct the volume of your images, your object, and increase the resolution in comparison to a standard electron microscopy. And so that's what we did. And as you can see, here we couldn't really see that there was a cell wall. And in the end, we can improve the resolution, see the cell wall, see plasmodesmata inside the cell wall connecting the two cells. And we can also improve the resolution with Eriscan microscopy, Eriscan module on the dice, to really have a very thin correlation between the two microscopy.
And as you can see here, to achieve electron tomography, we have to use fiducial gold particles. So it's another step.
Yeah, that could be critical too.
Yes.
That you can
Sometimes
destroy
the
your
last
sample.
step, yes, where you destroy your sample.
Okay. And with electron microscopy, it's very interesting because you can have the fine structure of very fine elements, such as plasmodesmata, and you can reconstruct them in volume, such as I will show in this video. So you can really access to the 3D volume of your region of interest. So of course, this was for a graph interface project, but now I'm using it on autophagy project. So it's to show you that you can apply this CLEM technique to other projects. And same as before, I'm targeting autophagy structure on fluorescence microscopy and transmission electron microscopy. Then I can do the correlation, find my structure of interest, and of course, perform electron tomography to have nice images. And now, thank you for your attention.
So hello everybody. So now we will speak about 3D CLEM. So I start with the technique of retomography. As you maybe already know, retomography allows to make 3D in both imagery by doing serial sectioning of the sample. So it's a technique dedicated to massive sample, but also to cells. Massive sample and high volume of sample. And there is I don't know if Stephanie, you can maybe stop your microphone, please. Thank you. Array tomography allows to explore a large volume of sample, like tissue, to obtain important information in ultrastructural level, and to target region of interest with a light microscopy, and to observe it after in electron microscopy with the SCM. Just a quick review of the workflow. So the basic step is that you are doing a fixation and then an embedding of the sample. I will detail all the steps after. Then you do serial sectioning that you put on cover slips to do immunolabeling, observe in fluorescence the different section with immunolabeling, so the different fluorochrome that you need. With this technique, you can elute antibody after to do other labeling, so you can do a lot of different targeting of protein or region of interest. Once you have finished with the fluorescence microscope imaging, you can do a post-staining to add some contrast to observe it with the SCM. Here again, you will observe section by section. So you will collect a lot of images that after you have to align and process to reconstruct a 3D volume. So the first step is one of the most important steps because you have to make a sample preparation. So if you have seen our previous workshop on immunolabeling, I already described the different way to prepare the sample. So here it's really quick. You can do a chemical fixation with aldehyde or a high pressure freezing, then dehydration and resin embedding. So we already speak about acrylic resin. So here it's the resin that we will use, so HM20 again, because it's dedicated to make immunolabeling on section. But we can also, as we can make different way to, we can have different way to go to the 3D volume and cells location. We can also use a protocol to do just ultrastructure in 3D. So, for example, here we use DAB to target the cells of interest, and then we have the GFP to detect the relaxin 3 axon in contact with some cells of, for example, here in this project of parvalbumin cell body. So once you have detect your region of interest, you will do a protocol that is at the beginning dedicated to do serial block face imaging. So Fanny will explain what is serial block face imaging just after. And so the DAB with the heavy metal will be dark on EM, so you will be able to detect the cells. And the epoxy resin and all the heavy metal give a better structure, so you will have really a good exploration of the ultrastructure. The common part is that you have to do serial sectioning, so it's the tricky part of the technique. So here, the first step is to make a pyramid. So we use a trimmer of 90 degrees to have very clear shape of the block. Then you will add some glue at the top of the pyramid, and when you will do section, all the section will stick together in ribbon, and in that way you can obtain ribbon of 100 and 100 section that you can put then on a support. So the thickness of the section is for us typically 100 nanometer. But it can be less or more, depending on the subject at the question and the volume that you have to explore. And we can collect more than 1,000 sections if we need, depend also of the question and the sample that we have. The flat deposit, it's absolutely necessary. So because on the SEM, it's better to explore all the surface of the sample. And that's why we have to have a specific attention of the support that we will use. So if we want to do immunolabeling, we have to use, for example, a glass knife with a carbon coating, but we can also use ETO, so indium tin oxide, but it's a little bit expensive, so glass slice is enough. But if you want to do just ultrastructure, so without immunolabeling, you can use a silicone wafer that is very, very flat and give a particular good results to make SEM observation. So here, once you have collected all the section, you have to do immunolabeling. So I show two different examples. This first one is on cell culture. So it was a flat embedding of cell culture. And for example, here you have the NEM 157 cells labeled with DAPI, EBP50 protein in GFP, and the actin in red. So it's just an example on one section. You can collect all this information section by section to have the 3D. Or for example, for this project, just stop here because it will improve the resolution in Z and help to make just fluorescence microscopy. And here it's again the project with the DAB. So you can see in fluorescence. So it can be fluorescence directly in the cells, but also protein label by typical protocol of immunolabeling. So I already explained all of these things. So once you have finished with the light microscopy, you go to the SEM. So for those who didn't know what is SEM microscopy, I just show a short scheme here. In fact, you have the beam that come in the top of the surface of the sample, and we will have different emission. And what is interesting for us here will be the backscattered electron, and it gives an image of the topography and chemical contrast images. So it looks like in TEM, but it's an SEM images. Here you see the different section that we had, and for example, we can target the different row of interest here with the Atlas 5 program from ZEISS. So you see in red, it's a different stamp that we had put to say to the program that we have here one section, here a second one. And then we can also help with the fluorescence that we have done on the same section just before, target region of interest inside. And the program will collect all the information that we need and all the different images quite alone after. So all the pre-processing phases can take days, but after it will do all the acquisition alone. So here it's a step where the contrast improvement is really important. So we can add, when we have done a process with HM20, we can add some uranyl acetate or some j'ai un trou de mémoire, le plomb, lead citrate, thank you. We have tested some different way to add contrast, but uranyl acetate or uranyl less are the best to help. as it's non-destructive because you will keep all the section after observation, you can come back after if you want to select another row, or if you have problem, or if you have detect that something is better in another part of the slice, or I don't know why, anything else, and it's okay. Alors, la vidéo, faut que je sorte. Mo, tu l'as mis où c'est dans quel truc la vidéo quand je te l'ai sortie? Ah, sur le bureau. Pardon. Là. Ah, oui, bon, ok. Et ça partage pas, c'est ça? Si, c'est OK. Ah, écran partagé, pardon. Hop, partagé. Donc là. So here you see a different section realigned, and sometimes you can see here the DAB, for example, the DAB precipitate for this case. So the different cells of interest in the volume. Yes. Donc, il faut que je nouveau partage. OK. J'arrive pas à repasser en plein écran, j'ai le truc. Ça va, tu sors? Ah, pardon. Merci. So, during the acquisition, you will collect thousands of images, and then you have to do, of course, image analysis. So here it's a result obtained by Thibault and Mark from the EMN. So it was made on a big number of sections. I don't remember the number. And you see in red the cells of interest and some different connections that we can characterize then with the 3D reconstruction. We already speak about image analysis. We can use different programs as Fiji or Elastic, but there is a lot of other one. And maybe one day we will do a specific workshop on it.
175 sections.
175 sections. Thank you, Thibault. Here, just to have a look, because I love this work. It's a work of Agnès Burel from Resin and his team. Is just to show that you can collect a really high number of immunofluorescence labeling to after correlate with the structure of C. elegans. And they also developed a glass knife dedicated to make a tomography. I didn't use it, but they make a beautiful development on it. To resume, the advantages of this technique is to collect 3D information in LM and EM, so or both or just one. So it's a tool very interesting to have 3D and to explore high resolution information. You can have multiple regions of interest in a large field of view, help with SEM observation, and there is no sample type limitation because you can do it on tissue, on cells, on animal tissue, on plant tissue, and it's not destructive, so you can make reacquisition. The limitation is, of course, the time that you need to make one experiment. It's really days of acquisition, so days of preparation, days of acquisition, so it's quite long. But now it's already automized for the SEM. We can have some limitation with the immunolabeling because of the process that we use to prepare the sample. So always the balance between chemical fixation, resin embedding, how to keep the structure, but to keep the antigenicity too. So in fact, it depends on the sample and the protein that you want to detect. And one of the limitations when you do this kind of protocol is the contrast with the SEM. At the end, so we are working on this project. We began like 2 years ago, and we had a lot of perspective because we have a lot of idea. So the first thing is to make an automatization of the light microscopy as acquisition, because for now we are doing it manually section per section. So I start some days ago to try high pressure freezing protocol, for example, on brain sample to help with the structure and maybe with the contrast. And maybe, or not maybe, but also with antigenicity. As Clément explained just before, we would like to try on some projects the in-resin fluorescence because it will help to localize the specific region of interest. And at the end, maybe in some years, we would like to combine it because there is already some work, especially in UK, to combine with tomography. So in fact, the section are also put on grid. So then you can have the region of interest on the section and go to the TEM and make some tomography. So to improve the resolution of the 3D analysis. I'm done. No, toujours pas. So thank you. If you have some question.
So good morning, everyone. Now we will talk about CLEM with serial block face imaging. So first, what is SBF? It allows us to obtain high resolution of 3D images from a large volume of a sample. As you can see, for example, here, three view SBF acquisition from the mouse earth block. You can see the blood vessel and the mitochondria and all the mitochondria. And just at the right, the reconstruction after segmentation of a blood vessel in red with the mitochondrial network in green. So we analyze the 3D dimensional context. How we can perform the SBF. At the platform, we use the SEM Gemini equipped with a 3-view. And more precisely, it uses an in-situ microtome with, equipped with a diamond knife. And it's a cycle of cutting, acquisition. And the specimen is automatically sliced by the diamond knife that you can see just here. And you see the pin with the sample on the top. And we have the backscatter detector, as explained by Melina just before, to receive the backscatter from the sample. So the pixel resolution is 10 nanometer in X and Y, and in Z is 35. The volume is 200 by 200 by 200 micrometer. The slice thickness can be between 25 until 80 nanometer, and we can acquire 100 images to 1,000 per acquisition. So we give us some example of tissue that we can use for a 3D CLEM. We can use a fixed tissue, but also cell culture on glass cover slip. And we can analyze, for example, mitochondria that we speak just before, or also a chromosome. You have an example in this paper. So how we can perform the correlative, or we can do CLEM with serial block face imaging. So first we speak about DAB. In fact, based upon APES injection in the region of interest, it allows us identification of apex activity in the transfected neurons expressing crepatide that revolves or cells of interest with DAB. You can see in this picture, in this image. And you have just here the reconstruction 3D. After segmentation, we speak about that at the end of the presentation. Another approach that we are developing now at the platform is near-infrared branding. It's, the aim is to localize the interest region during SBF acquisition. To do that, we use fluorescence to localize our region of interest, and we will increase the energy of the beam laser as to burn all around the region of interest. And we can modulate, we can determine the size of the burn when we play with the dose of pulsed lights. So we can summarize the workflow in 4 steps. The first step is to image and do the laser marks, so find your interest region. After we perform the SBF simple preparation for SBF, sorry. And then we do the acquisition, and the last step is image processing and analysis. So we go in detail for each step. The first one, localize your region of interest. So in this example, the region of interest is just here, and we choose the size of the mark with the post light that help us to recognize the region during SBF acquisition. Then we perform chemical sample preparation for with some specificities for SBF by adding some EV metals. Then we mount them on the block. So you can see just here the sample on the top in black with a pin and fixed with a silver resin. And then we go to the SBF. So what we see inside the SBF, you have a picture of an optical microscope where you can see the laser marks. And this is a schematic representation with the laser marks in white and our region of interest in red. You will have now a transversal view when we put on the pin, and you see in gray the representation of the view on the top of the block. And this representation is the representation that you see when you acquire during the SBF acquisition. And we know when we start the acquisition because we know the distance between the top of the block and the region of interest. And then we know when we finish because, as explained before, we choose the size of the laser marks and we know it's the end of the acquisition. And at the end, we obtain a stack of images and we perform the alignment. As you can see in this short video, all the images obtained during one acquisition. And the last step is segmentation. It allows us to measure the size, the number, but also to know the localization of our object on the 3D context. And just here you have an example that show the yellow cells, that tumor cells that polarize around the bile canaliculus that you can see in this video with the blood vessels. So it's a reconstruction, and segmentation will perform with machine learning, and also in this case uses the software ITK Snap. There are some advantages using SBF. You can analyze large volume, and you analyze the three-dimensional context. It is relatively fast, and it is a robust and reproducible technique. We can give some limitation. The Z resolution, it is a destructive technique, and also the equipment is relatively expensive. In this presentation, we speak about dab and laser mask. There is also technique to perform CLEM in SBF, for example, micro-CT, and we will develop it in the future at the platform. And also another possibility, the Collinson lab develop modify SBF microscope with adding an epifluorescence inside the chamber. I would like to thank everyone involved in this project. Thank you for the organization of the workshop, and thank you for your attention. If you have any questions, and don't hesitate to come to see you and to try at the platform.
And of course, you can email us to the BIC or to personal, the personal that is expert in the field. So now we are going to talk about the Cryo-CLEM workflow. I will be presenting the most direct workflow that is coming from a fluorescent specimen, and it's going to be really fast freeze. And then we are going to be for the acquisitions in cryogenic conditions in both light microscopy and electron microscopy, without labeling, without contrast, and without any kind of manipulation of the sample. So why not all the samples can be treated in this way? Because for this workflow, we're going to need samples that they are very small. From proteins and cellular fractions, so small organisms, virus and pathogens, to little organisms, tissue, not really thick. So the point here of freezing is because for the observation in electron tomography, we need to vitrify the water. What it means that is during the freezing, there are some crystals, ice that they are formed in the sample. And in this case, for example, you can observe by the electron tomography, and we need to avoid that because we can mask our sample, and actually also they can destroy the cellular components, the membranes, and the different compartments inside. So we want this kind of situation where the water is vitrified. So they form amorphous ice, and then then in this case the structure is the native ultrastructure is preserved, and also the specimen hydration, and of course it helps a lot to reduce the electron beam damage to the sample. So these samples can be these samples that I am presenting here can be divided into really thin samples, and they are up to 5 microns. And thick samples that we can also freeze up to 300 micrometers, not bigger than that. The thin sample that can be prepared by plunge freezing, actually immersing the samples in really fast in liquid ethane. And the thick sample will be frozen by high pressure freezing. So The plunge freezing method is going directly to the observation of electron tomography, but the samples, they need to be really thin, up to 100 nanometers, because the electron beam is not possible. There's no contrast, and you cannot see any more when the samples are really thick. So for if the samples are a little bit thicker than that, you have to go for a further processing of the sample, like for example here in Cryo-FIT milling, you use the near infrared branding of the cell components and to create a lamella, and then go into electron tomography, and of course MOVIS, that is actually cryo-electron microscopy of vitreous sections. So you slice the sections that are vitrified already. You recover these sections and you can observe them by the electron tomography. Of course, you can go for room temperature preparation, where you do freeze substitution, you use resins, and then you can observe regularly by TEM or FISM, as we said before. And the best option to use now, because we are to do CLEM in this condition, is to do cryo-fluorescent microscopy. And actually, we do that because in sometimes you need to localize the region in interest. Here, for example, for Cryo-FIT milling, to localize the region you want to observe. And also for sample screening, when you prepare a lot of samples and you screen your grids, and to localize very precisely the region of interest. So with the system we have for the freezing at the Bordeaux Imaging Center is a Vitrovolt Mark IV that is being borrowed by Remy Francis' team from the Institute of European Chimie et Biologie. Voilà. And the high pressure freezing that we have different devices, the HPM 100, and I think we are going to have very soon the ICE device. But I am not talking about the high pressure freezing today. Here we are going to talk about the really thin samples, small and really thin samples like whole cells, by plunge freezing. How it works? Actually, you have to deposit these samples in a small electron microscopic grid, which is covered by a carbon layer that is a whole carbon layer. And here you have different patterns of these carbon grids there are different brands like Quantifoil and C-flat. And actually you have to choose these holes depending of the magnification you want to do, the tomography you want to perform in these samples. What is your sample, if it's very small or is really whole cells? So you have a big catalog of this kind of supports. Then how it works, actually you have to take your grid with a tweezer, then do you deposit the sample solution with the biomolecules, or you make the cells growing on these grids. Then you have to remove the excess of water, and then plunge freeze your sample in liquid ethane by gravity. So in this case, as you can see here, a very well schematic, that your specimen is suspended in a really thin layer of amorphous ice film. So the parameters of the blotting and the plunge freezing are very important to obtain the best the optimization of this sample preparation. Once they are in the grid, you need to conserve the temperature in cryogenic condition to be observed by the cryofluorescent microscopy. At the BIC, we have two devices to do that. It's the Leica EM Cryo-CLEM system, which is a wide field system with a cryo chamber and a transference shuttle to introduce the sample in liquid nitrogen. And we have also a Lincoln CLEM cryo chamber that can be adapted to any kind of inverted microscope, microscopes. Like in the Pole Vegetal, they have a confocal microscope equipped with an iris scan detector. So we have a very resolutive imaging. So some examples of this protocol, this one is, for example, the group of the facility of the electron microscopy in the Institut Pasteur. Anna Sartori, she's a very good expert in doing this kind of workflows. She actually can use a protocol that is combining and to see what is what is the best approach to depending on what you are your question, a biological question. You can do everything in cryo conditions, in cryogenic conditions, and the fluorescence and the TEM, but also you can perform some fluorescence before going to freezing, and then do partially the cryogenic acquisitions in TEM. So here is an example. This is the two lines of neuronal lines that they are communicating each other, and they want to actually observe in more detail of what they are, what they call these tubular nanotubes, and what is the nature of these structures between these different cells. And actually, here they really find very precisely the region of interest with cryofluorescence. They use a Leica for cryofluorescence microscope normally, and they can really observe at a very high resolution for tomography. With tomography, the cargo components, and they are going from one cell to another. They can even discern the different cell walls between the cells, and also they can describe the different filaments that are in these structures, like actin and membrane connections. I wanted to show you this work from the group of Elizabeth Wright from the University of Wisconsin, that they actually use a device that we can use here in this facility, in our facility. They use the system of alveol to do the micro-patterning in grids to localize and to increase the probability of finding the region of interest. They do the patterning in the region where you can image, actually in the center of the grids. And then you can have all the cells that they are localized in these points. And you can even automatize the acquisition and go for tomography in the different hosts that you can find in the carbon. So they have some seminars in YouTube, and they are really good team to work in cryomicroscopy, Cryo-CLEM, sorry. And then I wanted to show you also this work that combined wide field microscopy with really high resolution microscope, where they use the same approach. They plate the neurons in grids, and they transfect them with different markers for excitatory and inhibitory markers, as you can see here in green and in red. And then in this way, they can discriminate the type of synapse that they are observing by electron tomography, and they can really describe with a huge resolution, nanometric resolution, the size of the different components of the synapse, like here the postsynaptic density, the difference between the distance between the membranes, the size of the synaptic vesicle. There are other structures that they haven't been observed before to this resolution. But they want, the interesting of this paper also is that it's a good introduction for our project here in the BIC, that they realized in situ single particle analysis, where they observe with this powerful microscope the different proteins that they component in the membrane. Like here, they claim that they are glutamate receptors, but they don't have really specific information about these glutamate receptors, but they can actually discern the differences between the receptor by this little C-tail inside of the cell. So it's amazing how they can see it, but they don't have the specific information of these receptors. So that is the perfect way to introduce a little bit what we want to do in the lab. Here also you can see the differences between the resolution of a wide field microscope and the hyper resolution, nano resolution of the electron microscopes. So I wanted to introduce you in this work of the laboratory of Grant Jensen in California, in the Caltech, where they prepare this kind of grids also with bacteria, and they make them express this protein. I cannot control the video. I don't know. No, I cannot control the video. So anyway, in this case, what you have is the difference in the resolution when you express this protein. That this protein you can do cryo-CLEM because you can control the activation of this protein. These proteins are photoconvertible. As you can see here, we have a whole workshop dedicated to super resolution from Magali Mondan. I am not going to go into the details, but actually this whole protocol realizing the property of these proteins to be controlled by light and the activation, and then we can see the activation in different space and time, and then we can really localize them very precisely. And in this way, you can see in here in these tomograms how they can localize the region of interest for the tomography, and observe in very high resolution, in nano resolution, the actually a structure of this protein of interest. And that is the combination, thanks to the combination of super resolution. And I'm sorry, because I cannot control the video. Normally, I wanted to control the video to show you a little bit faster what is the final result. They localize this region very precisely, and then they show what is the structure of this protein by a single particle analysis. And you can see here. So the point is that many people here in the Bordeaux is interested by this approach because they want to really localize very precisely their protein of interest and to see to do single particle analysis. We have a big community of people that do single particle analysis in Bordeaux now. So with the help of William McGreeny, that is a really good engineer that goes through the microscope we are using right now, and Magali Mondan, which is the expert on super resolution techniques. We started to do sample preparation for this kind of approaches. We grow the grids, the cells in these grids. We transfer them with a different construct to do cryo-CLEM, and then we freeze them with a vitrobot. We transform our commercial setup, Leica, in a cryo-CLEM system by installing different laser lines, filters for PAM. Of course, to monitor the acquisition by micromanager, and then we use also a camera more sensitive and more powerful than before. So now we use some of the constructs from Gregory Janon, that construct that they already characterized by room temperature, and this actinin is very nice because you could see the focal adhesion in cells. And then they are tagged with a protein that is photo switchable with light. In this case, you can see the video. Also, if I could activate the video. Okay, oh, sorry. So yeah, so this is what it looks like when we see it on the white field in the grid channel, and then when we activate these molecules, we can see that they are randomly blinking in the sample. We can detect it by a dedicated software, and then try to reconstruct after thousands of images like that the whole structure of the different what protein forms. However, you can see here that we gain a lot in resolution. We are going from wide field and low resolution images to a high resolution by cryo-CLEM. Well, but we can actually affront the different stability issues because we need much more images than we do in room temperature, because there is some changes in photoconversion of the proteins. So we need a very stable microscope. We need to also, of course, to develop a software that is going to bring us to electron tomography to localize the region of interest, and then to control the microscope to go and to do the picture in these places. And for that, we need collaborations with the people from the community of the single particle analysis and electron tomography in the Institut Européen Chimie and Biologie. is the team of Remy Francis that coordinate a whole project. We apply for the NECIPES 2020, and then we obtain the funding for doing this kind of progress here at the Bordeaux Imaging Center in collaboration with them. So, and this is what we are doing right now. Of course, we are finishing today the workshop. If you have any question in this workshop, I would be happy to answer the questions. Before, I would like to thank you all the components here today of the workshop, but more especially Magali, that has been working really hard in coordinating and organizing these workshops, the meetings and all the really emails that they've been sending. And Fabrice, that has been here, you've been hearing here in one side, that is always helping registering and recording and helping here around and listening to us. I don't know how we make it. And of course, all the whole Bordeaux Imaging Center that really, they believe in our workshop, in our workflows of CLEM. So, if you have any question, don't hesitate for any this workshop, this presentation or other presentation during this workshop. There's no questions.